Okay. So our second speaker is Professor David Gamarnik from MIT. So he's now full professor of operations research at MIT, and he received his PhD in operations research at MIT, and is widely recognized for his contributions to applied probability, stochastic processes, and the theory of algorithms. And his research is mainly about fundamental questions in optimization, both classical and quantum, random structures, and computational complexity. And he got several prestigious awards, and also he's been a leading voice in assessing the limits of algorithmic performance, both for classical computing and quantum computing. And today he will talk about quantum overpromise for optimization.
Thank you, David. Good afternoon. Good to be here. Thank you for Giacomo for the invitation and the fantastic opportunity to interact with the audience in this kind of a less than technical way, and that's the way I want to sort of keep the talk in spirit. So first, as a disclaimer, I'm the least qualified among the four speakers here. I'm the least qualified to talk about quantum technology. This is a relatively new field for me. I've started working on this about maybe 5 years ago, and I'm 57, so it's really I don't know what I'm doing. So for I take my hat off to my colleagues. They know much more experience, much more knowledgeable. My field of expertise is more in the whatever is called optimization. That's what I want to talk about primarily. So I don't know much about quantum science, but as the joke goes, I don't know what it is, but I'm happy to explain it. Just to explain the figures, this is Richard Feynman and this is David Deutsch. These are founding fathers who conceptualized the idea of the quantum computer. And this is versus Alan Turing, was obviously founding father of the classical, as we say, conventional computers. So this is my outsider's perspective on the quantum computing. I think this is one of the greatest scientific and engineering challenge of our time. This is what personally brought me to the field. When I learned about the questions, mathematical, algorithmic, business, or across any way you look at it, as a scientific and engineering challenge, it is amazing. At the same time, I don't think it's a good investment opportunity. So if you're thinking about buying D-Wave machine to churn money, make profit out of it, I would say, think again, right? And I'll try to justify my position on this through the lenses of the field called optimization. So if you already bought it, if you already invested in big, giant quantum computer, I would say, thank you very much, because you're doing a great service to the society by advancing the science and technology and helping folks like my colleagues to do a great scientific discoveries. But please do not expect, despite the hype, I want to de-hype it, don't expect that this technology will churn money soon. And let me justify and explain why I stand on this position. And as the time goes, the more time goes, the more stronger I stand on this position. It's also a limited perspective, so I want to also sort of premise it by that. If you read about popular description of quantum promise, basically, where do you expect the quantum computers to make the greatest dent? Basically, where do you expect them to be the most kind of effective? You would find perhaps the following areas. One often quoted area is the quantum chemistry. I'm not a specialist on that, so I'm not gonna. I'll be careful about sort of commenting heavily about that. However, if you dig down deeply into that, there's something suspicious about the promise of the quantum progress in the quantum chemistry as of now, and I'll explain what it means. The second often quoted, and this is what brought me to this whole debate, area is the so-called optimization, and that's the area of my expertise. So I'm kind of qualified to say something about that. But there are other areas, cryptography, That's the previous talk. That's, fair game. So I'm not gonna, obviously comment on that. We already heard a great talk just before. Finance and investment has been often quoted as, for certain reasons that we will discuss, as one of the most promising area of application of the quantum computing and quantum technology. And I'll say why, but not now. And last but not the least, but this is not the full list, but last in my list is artificial intelligence. It is quoted and it's stated many times that quantum technology is extremely promising, specifically in the areas of machine learning and artificial intelligence. And if you dig deep into that, and we will to some extent, we will see to what extent we should actually expect that to be the case. All right? Okay, so I guess I'm kind of a Mr. Negative here. And as Giacomo already said, I also work on classical negative results. So now I'll move to the quantum negative results. So maybe some people hate me for that. I'll take it. Let me do a gentle introduction to the field optimization. Optimization, well, optimizing something that is very natural to us. We want something better, best, and so on. But it's actually a scientific field. So let's do a quick walk over that. What is optimization? We use optimization in our daily lives all the time. So if you use the GPS and find the shortest route between A and B, that's optimization. Well, it's done it's done for you on behalf of you by the technology, but it's somebody somebody is solving this problem for you. How to go from A to B in the shortest time. You go on a trip. You try to pack the largest number of useful items in your bag. There's a limited capacity, but you want to make the most usage of it, most utility of it. That's an optimization problem. Internally, you don't think of it maybe this way, but in fact, it is a special, an example of optimization problem. Or you try to manage your money in best possible way so that you optimize your portfolio return. This is admittedly a little American-centric here as an example, but probably here as well. It doesn't mean that you solve this problem, but maybe professionals, financial advisors solve those problems for you. But optimization is also a huge multi-billion-dollar industry because it's used across the board. Historically, the earliest use of optimization is in military. I'll talk about that. In airline scheduling, transportation, Uber and Lyft rely on very sophisticated version algorithms for optimization all the time. Facility location, online advertising. When Google decides which Google, Facebook, any online social media, when decide which ads to put, there's a deep complicated algorithms to figure out what is the combination of online ads that will make the most money for the company, right? Workforce management, financial investment, as I mentioned already, and many other examples. Okay, it is a scientific field. It's a mathematical field, and it's actually pretty old. I'm not a historian, but sort of roughly speaking, one could say that the earliest scientific approach to optimization goes back to Newton because he invented calculus, right? And maybe you remember. I know I'm not supposed to expect you that you have scientific degrees, but maybe calculus and derivatives. How do you find the largest point on a curve? You set the function, derivative, and you see which point gives you the largest value among the points that have derivative equal to 0. And this is how you do that in high school or college when you take calculus. But in fact, in modern usage of optimization, perhaps there's a new phase or era of optimization that started after the World War II, when George Dantzig invented something called linear programming. Linear programming is called programming, but it's not the programming in the sense of coding. It's a programming in the sense of the algorithms. He was solving a big transportation logistics problem for Navy. He was trying to figure out how to best ship the whole bunch of different items to the Navy locations. This was 1946. And he figured out a very clever algorithm to do that called linear programming. And that's the beginning of the modern scale. Why is it that application important? Because it's the first time that optimization was thought in terms of a large scale kind of big data type of environment. Here you're really optimizing over one variable. It's kind of it's like smallish that enough that you can do kind of by hand. Starting from this area, optimizations are solved with a huge number of different variables and possibilities. As it turns out, I promise this is going to be the only math in this talk. Optimization, it's a principal scientific field because you can reduce it to some extent, you can reduce it to the case of linear or so-called non-linear optimization problem, which looks something like this. You try to maximize some quantity, like the value of your portfolio, but you have some constraints, like you don't have more money than you have. And then you write down those constraints and so on, and then you give it to the computer, and then hopefully you have a good algorithm, and the computer toggles those numbers, makes sure that constraints are satisfied, but tries to make this as much as possible. So that's an example of optimization problem. But let me give you an even more concrete example. Here's an optimization problem which does not involve any equations. It's really a game, very simple one. You can play with your kids, right? I tried it with my daughter. She didn't like it, but maybe you have a better luck. So you have circles. It's very simple. You have circles and you have connections. These are like, think of them as members of the social network, and connection means that they're friends. Okay? And your goal is to find the largest number of non-friends. Right? You want to find the largest number of non-friends. Why? Turns out that this has many applications in various across the board. Let's leave it aside. This is a really interesting practical optimization problem. Right? Find the largest number of circles. I'm not going to torture you how to do that. I'll just give you the answer. In this case, you can just manually sort of play and find out the combination. So it turns out that you can find 10 out of 16, and notice that I did not violate any constraints. So no two blue dots are connected by an edge. All the blue dots are non-friends. By the way, if you have any questions, I'm happy to pause and answer questions during the talk. No need to wait till the end. Okay, let me give you one more example. This is an example that I use with students when I teach optimization at admittedly very elementary level. This is a really portfolio optimization question. So suppose you are considering investing into a combination of 20 projects, and you have investment amount. And you have a budget $220 million, let's say. You can invest up to $220 million. This is the invested amount for each of the projects. So this project would cost you $13 million, $30 million. And so of course, you have to stay within the budget. And you want to maximize the profit, and the predicted profit figures are reported in sheet. Okay? And the question is, what's the best combination? Believe it or not, you can solve it on Excel in a split of a second with optimization technique, non-quantum, very elementary. You can solve it in split of a second, formulate and solve it on Excel. Excel has optimization method, optimization algorithms, and that's the best result. Turns out that you need to invest in project 2, 3, 6, 7, and so on and so forth. This problem involves 20 so-called decision variables, numbers to toggle. But modern optimization applications involves thousands, tens of thousands, and millions of variables. And Gurobi, one of the leading softwares that, the leading software in this area is Bologna. We can handle millions of errors. And that's the scale that companies really need to solve those problems in applications. So these are 3 examples. There's more examples. I could give you more. The list goes on and on and on in airline scheduling, in project matching, and finance, and so on and so forth. So where's the quantum promise? Why is that? Why do we could believe that quantum computers could give us the edge over conventional computers in solving these kind of problems, large-scale problems involving thousands or millions of decision variables, right? This is not. Let's try to understand it, right? It's not a very dumb idea. It's actually pretty clever. There are clever reasons why one would expect something like this. At the very least, let's think about the skills of conventional computers in terms of, for example, the memory capacity versus quantum computers. I'm going to do that without introducing the formalism of quantum computing. I will just tell you the implication of what the quantum technology can do, for example, in terms of the number of states that it can encode. So the conventional computers, if you have n bits, you can encode 2 to the n different states. And this is how sort of your memory scales. This is why we quote memory of your computers in terms of, gigabytes, terabytes, and so on. The terabyte is that many bits, and modern PCs have about 2 to 1 to 3 terabytes of memory. Now, the fascinating thing about quantum computers and quantum technology is that the number of states that it can encode, roughly speaking, I'm not very precise here, my colleagues might correct me, but roughly speaking, it grows doubly exponentially in the number of qubits, which is the quantum analog of a bit. Right? The number of configuration, because the quantum computer, as you may have read, if you read something about that, it works in a superposition of states. It works in the superposition of the classical so-called bit configurations. I have a picture to illustrate that. But just to appreciate this sort of the growth, I've put some numbers here. So how much you can get with qubits versus bits. So with 5 qubits, with that kind of growth, you can get that many states. So with 10 qubits, this is equivalent to the 1,000 conventional qubits, because 2 to the 10 is about 1,000. So that's the growth. And if you have 40 qubits computer, that can encode anything you want, potentially. With a scale like that, it makes very reasonable that if the computer can juggle such massive things at the same time, it should have an edge. So that's the idea. It's a very reasonable idea, no? The way quantum, but the scale by itself is not the answer, right? The way quantum computer works, and this is just one quick slide, and I'm not expecting you sort of to parse through this in detail, but the way quantum computer works is that it creates a superposition of classical bit string configurations and starts kind of rotating them in some way. You engineer, your algorithm is supposed to engineer to rotate them in such a way, such that in the end you obtain configuration which, after so-called measurement, produces a good solution. What is a good solution? Optimal portfolio, optimal dots, non-friend configuration, whatever is your optimization problem, or whatever is the problem that you're trying to solve. Because the quantum computer can operate, it's kind of like operating on all solutions at the same time. You just have to rotate it cleverly enough so that it finally arrives at the solution that you want. But then you have to engineer it so that it arrives at the right solution. Can you do it theoretically? Can you do it practically? That's what I want to talk next. Right? There is a reason for optimism. First one, let me lay out why it would be reasonable to expect the supremacy, as is often quoted, of the quantum technology. Supremacy means advantage. It's a term coined by John Pascal, very nice, clever term that captures the idea that the quantum computers should be supreme, more effective than conventional computers. What is the reason for supremacy? One thing is memory. We already talked about that. There's many success stories. Perhaps the most famous one is the celebrated Shor's algorithm that gives a quantum algorithm for factoring numbers, and it's a staple of cryptography that to the day, no classical, no conventional algorithms can match it in terms of theoretical performance. Shor's algorithm is not yet practical because to make it practical, you need way many qubits that we have currently. But theoretically, it's a startling achievement. There's no doubt about that. It's not the only success stories. There are other success stories, like maybe lesser known, but so-called Grover search. I'll skip what it is. And there are other stories in terms of the sampling quantum states, supremacy, and so on. Offline, I'm happy to talk about that. On the practical side, there is also big progress has been made in terms of building stronger and more larger quantum computers. And nowadays, the figure I see quoted is about 500 to 1,000 qubits. Of course, we understand that the number of qubits does not directly translate into the performance and optimization, but the more the better. No doubt about that. Many companies spring that invest almost exclusively in building quantum technologies. Some listed in here, some maybe usual suspects. Many companies build research groups, like many finance companies build research groups. Amazon has a quantum research group. JP Morgan has quantum research group. Major investment banks in the US, maybe not only in the US, build quantum groups. Why do they do that? I suspect they anticipate some kind of fairly quick advantage edge in solving the problems that they care about. We'll see if this is something that's actually justified. And what perhaps bothers me even more, quantum supremacy is often quoted as a present-day reality. Almost on a daily basis, I see Google Scholar recommends me based on what I care about, my reading and what I work on, recommends papers that claim construction of the quantum algorithm that is stronger theoretically or practically than conventional classical algorithm. And that was now a bit of a red flag for me. So I decided, okay, I need to understand what is going on. To what extent these claims are actually valid and justified. What are the issues with quantum technology? If you read about the challenges, one of the most quoted one is the issues of the robustness and the coherence, engineering challenges in making the computers fault tolerant, error free, and so on. And a lot has been said about that. I'm not going to comment on that. That's a definitely big challenge, engineering challenge that needs to be addressed. And I hope that sometimes this will be addressed. But that's not the issue that I want to discuss today. One of the issues that I want to discuss today is benchmark. When you say that your quantum algorithm or my quantum algorithm, somebody's quantum algorithm is better than conventional quantum algorithm, how do we do this comparison? What do we compare? Right? This seems like should be an obvious. It's not a very obvious question. Benchmarking is actually a pretty tricky thing, and even within the classical conventional computers, properly measuring performance of one algorithm versus another algorithm is science by itself. It's not a very straightforward thing. Number two, as it turns out, there's also theoretical barriers for quantum algorithms in the field of optimization, at least within the so-called NISQ type, noisy intermediate type quantum devices, quantum systems, within which is a class of quantum algorithms for optimization, which is supposed to be built pretty soon because it involves less, it doesn't require that much fault tolerance and so on. We'll talk about that. Turns out that there's a theoretical barriers to that, and that's my line of work. Barriers which apply to both quantum and classical algorithms, in pretty much mathematically meaning that quantum computers cannot overcome those barriers, but below those barriers, even classical algorithms approach those limits. So that leaves almost no space for the quantum improvement. I'll give you an example shortly about that soon. False alarms, I already talked about that. The evidence for the quantum supremacy, for the optimization, I want to stress, I'm talking about optimization areas, is quite shaky because of the benchmarking issues. You start digging deeper, sort of what does it mean that this algorithm is stronger and so on? It's not entirely clear. The other thing that I got to appreciate, but not immediately. So I've quoted several areas of application for the quantum technology: quantum chemistry, finance, investment, and AI. But if you dig deep into those problems, what exactly problems quantum computers are supposed to solve for these particular industries, it turns out it's all about optimization. Because in quantum chemistry, it is about finding for something called quantum Hamiltonian, the ground state of quantum Hamiltonian. That's an optimization problem of a peculiar type, a difficult one. It's not an easy problem, but it is an optimization problem. Finance, it's a portfolio optimization, either portfolio optimization or computing financial derivatives. These are optimization problems. So if there are limitations of optimization problems in general, I would not expect that the finance, by some miracle, would be better would be better off because of the quantum technology. AI. Why do we expect that quantum computers are particularly promising for AI? The quoted reason is stated as because we can use it to train neural networks. You might have heard the term training neural networks. You adjust the weights of the neurons so that they fit and the data the best and provide a good generalization and so on. Training neural network is sort of a name of the game in across the board in machine learning. What is the training? Training is optimization. You're trying to adjust the weights of the neural network so that you minimize the so-called loss function, and that's a minimization problem. Feeding to the data so that you have a good performance for your large language models and so on. That means minimizing loss function. That's a minimization problem. So all these quoted areas that have been quoted, in fact, are about optimization, not cryptography. That's a separate game, but others are. So let me talk about benchmark. To do a proper comparison of what the quantum computers can do for the optimization versus classical computers, we need to have a proper benchmark. We need to figure out how do we compare, that we compare apples and apples. When the quantum supremacy is being claimed, the nature of this claim is usually of the following kind. We ran our computer in much less time, and we have a better performance, better objective function, better value. Well, how do you measure time when it involves the quantum computer? That's not entirely clear to me. Because time is time, right? So even two different conventional computers, time, sometimes you have to use the CPU clock or something like this, but for quantum computer, what do you use? It's not entirely clear. There is a more honest way to do that, and I'll talk about that, but it's not done yet. And I doubt that the quantum computers of the day today will actually perform well in those in this proper benchmark. Benchmarking is an old story in my field of optimization. Pretty much this optimization was arrived. When optimization became such an important game, what happened was the sort of a community created a whole bunch of so-called challenge problems. These are particular examples, instances of optimization problems that anybody can try to solve. And it's a competition who does the better. So one example could be like a big giant network in which you need to find the largest number of non-friends. It's called the independent set problem. That's a technical term. Another one could be like, who can solve the logistics problem the best? Another could be, who can pack the largest number of entries in a giant kind of a bag? Or who can solve the finance problems? And list goes on. So there's a list of problems, and people compete. They come up with the algorithms, they can compete. One of the most celebrated, maybe, examples of this is something called the Netflix challenge. Have you heard about that? Netflix challenge. That's a challenge that was 10 years ago when Netflix gave its data and said, find me the best way of predicting the rating by the users in the movies. They depend a lot on the good quality predictions. Turns out that's an optimization problem of not too different from the dots packing in a network. So people compete, and the winners got $1 million from the Netflix, but it's just one of the many examples. You have a good algorithm, show that it works. So one of the organizations that runs this is called Timex. They pose these problems, and people compete. And there's teams and teams and teams that they compete, and some are better, some are worse, and so on. So the compelling example would be if there is a problem for which somebody with quantum computer or combination of hybrid version, quantum and classical computer, can come up with a solution better than any other solution so far. Then it would be fairly objective thing. By the way, this is exactly what happened with neural networks. When Jan LeCun reinvented neural networks, what propelled him to celebrity was the fact that his new version of the neural networks did a better prediction on images by 10 and 50% than any other competition. And then, science or not science, he's doing better. This is something to pay attention. That would be very compelling. Only recently, because there was so much kind of a false alarms in the quantum supremacy in solving optimization problem, then people got together, and this is one of the recent publications in August. It's about suggested benchmarks for quantum algorithms to compete. So it gives a big list of problems and says, if the quantum computers are good, try it on these kind of problems. These are particularly good problems for the quantum computers to solve. It involves something called cubic or quadratic constrained binary optimization. Because of the physics connection, that's the particular nature of the problems in optimization that quantum should work well. Good. So, and practical advantage of the quantum computers solving those problems is questionable. I'm going to jump out of a little bit here. So I have a couple of slides here. Even though it's claimed, as I said, almost every I should mark the time, right? So how much time? When do you want me to shut up? Okay, 5 minutes. Okay, I'll keep it. I'll keep it in 5 minutes. Many papers that claim the supremacy as a present day reality, and this is I find it mind-boggling. But there's also theoretical barriers. Maybe in the interest of time, I will not go, even though I don't want to indulge too much into my own line of work. But basically, you can show mathematically there is a certain limits on what quantum algorithms can do. And yet there is so much belief, almost religious belief, that quantum can bring about advantage over classical computers for the optimization problems, that among very respectable colleagues. It's not like I'm not talking about crackpots. Really, I'm not going to say names, but with the very, concrete, very respectable people who absolutely believe they can build a quantum algorithm that beats the classical computers. It's almost as a religious belief. But what happens is that usually when they prove something, somebody else comes and say, you know what? In fact, we can have a classical conventional algorithm that does even better than your quantum algorithm. In that case, okay, but we will try this problem now. And then somebody says, no, you can actually, we have more classical algorithm. So that's kind of a game. We'll try this, try this. This reminds me, I cannot resist temptation. I'm in Italy, so this is this is a scene from my favorite movie, La Dolce Vita. I'm sure you know this movie, right? But Federico Fellini. So in this movie, as you maybe have watched it, there's an episode where two kids claim they've seen the Virgin Mary, apparition of Virgin Mary in the air, and say, we've seen it. And the whole town goes berserk. They run after that, the police is involved, people are fainting, there's a massive praise, and so on and so forth. And long story short, turns out the kids made it up. They're kids after all. But the public is not despondent. They say, okay, this was a hoax, this was not real, but I'm sure there's going to be another apparition of Virgin Mary. We will just keep searching. And this is sort of what reminds me of what's happening with the quantum dedication to find a quantum problem for which the quantum algorithm will build a classical algorithm for optimization. One of the reasons, very quickly, one of the reasons that particular type of quantum computers cannot build the classical computers is that, especially when they're in the so-called NIST regime, is because they're effectively localized and they cannot see the full network. And we have a paper about that let me pull the paper. It says QAOA quantum algorithm needs to see the whole graph. The point is that for certain type of problems, like the packing the nodes without the friends, you cannot solve with optimality unless you see the full network. For example, you might not even distinguish that the fact that this network is for example, a dating network, and only connects boys to girls and girls to boys. When it's the case, you can pack half of the nodes. Half of the nodes, boys, are not connected to each other because they're connected to girls, or all the girls are not connected to each other. So optimal solution is half of the network. Without that structure, the optimal solution will be way, way less. Quantum computers cannot distinguish between the two because they're localized. The rest is mathematics. Let me wrap up and sort of share my thoughts on this. These are my only my thoughts. I am a believer in quantum computers and quantum technology. I think when they're built, it will be amazing. I just don't think that optimization and its sister versions is the right challenge for that. I don't think we will see the advantage in those problems. And for that, let me share with you another type of supremacy. I call it abacus supremacy. What's abacus? Abacus is this counting device. It was invented in Egypt. You probably know what it is. My grandmother was a bookkeeper. She had abacus. She could count. She could crunch the numbers very quickly. This is a very efficient. This is a very nice device. My grandmother was not a great mathematician or anything. She just learned how to do that. And if you give a challenge to two people, one with abacus, one without abacus, abacus wins. No doubt about that. You cannot do in your head calculations that you can do with abacus. Nobody needed to prove supremacy of abacus. Nobody needed to find some exotic problems for which abacus was better. It was just obvious. It's in your face. You see that it's stronger. And I think when the quantum computers are built, their advantage will be demonstrated in a very mundane task, like adding, subtracting, search, sending text, and not on those exotic and sort of peculiar and sophisticated problems like financial investment and derivative pricing or airline scheduling and things like that. That's prediction is a fool's errand, of course, but that's, I think, what that's the instantiation of the quantum supremacy that I anticipate will happen. Thank you for letting me share with you these provocative thoughts, and happy to take questions. Your thoughts.
Yes. We have a microphone for questions. Okay.
I would be very interested to know, like, one of the examples of how benchmarking is used when trying to compare computers and quantum computers, because since they're two different kind of objects, it does not seem like trivial how you would compare which one is more efficient.
That's exactly the reason why. That's exactly the reason why doing this comparison is tricky. So when I said use those benchmark problems, it's basically a good challenge for any kind of problems. So there's a benchmark instances, and people compete and they come up with the best solution, and there's the best current solution. It gives you X. If you come tomorrow and reveal your algorithm, which happens to be quantum algorithm, or it's a combination quantum and classical, and it goes from X to X plus delta, good. That would be already compelling, because now we would know that somehow this advantage was obtained by the quantum device, right? And I wouldn't even need to worry about timing and cycles and things like that, because as you absolutely correctly said, it's not even clear how to compare or do those comparisons. So I'm just suggesting to compete in app by